Hi, my name is Yin, and in about the next 40 minutes, I will share with you my knowledge and experience of my journey down the road in artificial intelligence. So without further ado, let's get started. So let's do a quick introduction. Who am I? My name is Yin. I come from China, and I came here in the United States in 2010. That was the time when I was pursuing my undergraduate school at the University of Rochester. I got my math degree in 2014, and then I worked a year on Wall Street as a trader, and then I went back to school to get two more master degrees. And now I'm a professional data scientist at Bayer Crop Science. I will be going back to school and leaving the industry that I really like in the September to pursue a PhD in statistics at Columbia University. That's essentially a highlight of my background. And in terms of artificial intelligence, I do research mostly focused on machine learning and deep learning. And there's one big motivation for me to do this, to be here to speak to you guys, is when I was on the journey of pursuing artificial intelligence, I actually have seen lots of roadblocks, and those roadblocks are there to stopping me from moving forward. If I had someone there to guide me to point out these roadblocks, I would say that this journey down to machine learning and artificial intelligence is going to be much smoother. So with that in my head, I said to myself, hey, if there's ever a chance in the future that I can come back to put this together in a video or in a document or in a journal that I can tell other people, then I will definitely do that. So here I am to put together some of the important highlight and knowledge that I've had throughout my journey in artificial intelligence. So the presentation is going to be structured as a Q&A session, and the questions are collected not just from myself, but also from network in academia, network in industry, as well as online social media such as LinkedIn and that sort of stuff. I would say one of the biggest question I've seen in artificial intelligence is that people tend to be binary about this kind of topic. You see, from talking to people in the past 3 to 5 years, it comes down to two types of visionary. The first one is fear. AI will take control of everything, big data knows everything, government is looking at us, that sort of thing. Conversely speaking, there's also the pro team, right? The pro AI. AI will do everything for us, and that's just going to be the future. I would say neither of those visionaries are accurate. It's most likely not going to be binary, right? Chances are it's going to be a spectrum. People who are on the edge of that spectrum is not able to look at this topic from all perspective. You really want to step aside and really absorb what you can learn from all different angles. You can think about in the past days when Ford introduced mobile cars. And before that, people travel through carriages, through horses. Yes, when you introduce cars, the jobs that are running the carriages are going to be gone. And yes, that's a sad thing to put some other people out of jobs. But eventually society as a whole will move forward much faster and much more efficient. And the people will eventually pick up the knowledge to learn about driving cars. And that's why today you see most people have driver's license. So that's one thing. And another thing is most people scared of big data, most people are scared of computer vision. No, I'm not saying that they don't have any danger. Any kind of technology is a double sword. Depends on people that use that. So completely shutting down the R&D of the branch of research on national level sounds a little bit too irrational to me, right? You definitely need people behind the screen or act as a stakeholder or authority to come together to put some sort of protocols in action so that once this technology is out there, if someone sees an advantage to abuse this technology, he or she may be stopped. If he or she may not be stopped, then there better be a punishment if this technology is used to harm other people. So with that said, I do believe that our government is doing that. It's pursuing that route, and it's taking all these big corporations into a room and check their books, check their files, check their algorithms. And I think to some extent they are doing that. Exactly how that's carried out, I don't know. I don't work for the government, I have not worked in the government before, and I don't know how that's carried out. And this is to diverge our conversation into a tangent. I would say that to fight the people who abuse this kind of technology, you really need a better technology to do that. I'll give you an example. Online, there's a branch of research called deepfakes. It's actually not a branch of research per se. It is an important branch in computer vision. And it's a very complicated application of this technology called convolutional neural network. So on top of that, people also diverge from a convolutional neural network all the way to variational autoencoder. Um, and then there's some other fancy stuff built on about that. So really, the entire computer science community as a whole is able to do a lot of the things with images, with videos, with audios. And these technology are all out there. They are able to just take a chunk of audio or video and turn that into something else. It looks like somebody else, but really it's not. That person was never there. So to fight this kind of abuse of advanced technology, you need a better technology to do that. It's not about a bunch of lawyers come together and they're all well trained in industry and all have experience and they can magically get this case solved. It's most likely not that. They really need a tech consultant on the case to really break down and diagnose that chunk of video, to use the tools that these people use to create this kind of video and use that against them. That's going to be a much more persuasive argument on the case to protect the people from the content that they brought up against them. So something like that's definitely worth our attention, and I definitely believe that we are walking down to that route. And in the US, we do things very carefully. We are a rather democratic country, and people have their voices heard. So I wouldn't worry that much about this part. I will certainly not use that fear as a roadblock to stop me from moving forward down to the journey of artificial intelligence. Another interesting question that I got asked all the time is, how do you get this journey started in machine learning, in data science, in artificial intelligence? Now that's an interesting question, right? Because there are so many different ways to get this journey started. Me personally, I hope to see a world where money is not a problem when people get this journey started. Unfortunately, money does play an important role when this journey gets started. Although it's not black and white, but let's break it down as much as we can. If you want to get your machine learning and AI journey started, you really need a good education. And unfortunately, good education is not free. From what I'm seeing online and on these course catalogs of top 30, top 50 universities, most of the cutting edge technology are still preserved and maintained in the top 10, top 20 universities. That's unfortunately a cold hard truth. The people who are high in power, the people who are high in ranking, they still have hold of all these knowledge that it's either A, they're not sharing, or B, even if they share this knowledge, they get the paper published, it's going to be very difficult to understand that. It's unlikely that a high school graduate can just magically understand a paper published by LeCun, right? And that takes time, and that time is not free. You need to pay for that. You need to pay for that with energy, pay for that with cost, pay for that with money, pay for that with your life. Essentially, you need to go to school to get that figured out. Initially, I would say if you're high school students and you're watching this video, I would probably focus a little bit more on math. I wouldn't struggle too much on grades because as far as I've seen, high school grades don't play a big role in my journey, at least. So I wouldn't pay too much about grades in your high school. I would just focus on truly understand some of the math that the school is teaching you. And if you can do that, that would be great. If you're in college, I will say to get this journey started, you really need to have a strong math background or computer science background or stats background. And I think these are the areas that it will eventually help you a lot. Most of the knowledge, most of the materials in math, stats, computer science are actually come from famous textbooks, which are essentially extracted from papers, either 10 years ago or 20 years ago or 30 years ago. If it's math, it's likely that's longer, many years ago. If it's stats or if it's computer science, it's probably going to be a little bit younger. So with that being said, in college, I will say that these three fields are going to be the foundation to help you guys get started in machine learning journey. Now, but that being said, machine learning, I think end of the day, it's really about collaboration. No one can magically finish thousands, tens of thousands experiments by himself or herself. End of the day, the experience are passed on much faster if you just talk to someone. That's also why we are here doing this, right? But all jokes aside, I think most of my knowledge and my experience accelerate the most because I talk to the more experienced people. They're professors, they're PhD students, they're grad students, they're people in the industry who have 5, 10 years experience. They are there to tell you their life story about machine learning and AI journey. And they are there to have all different roadblocks either solved or they somehow walk past by it that are very valuable for you to pick up. I'll give you an example. This is one data set that I play around with. Without having a whole lot of background knowledge or industry experience about what a data set is, your options are really limited, right? It's like you're trying to swim, but your feet and hands are both tied. And that's not a good thing. You don't want to do that. You don't want to put yourself in that situation. And if you're ever in that situation, you want to figure out a way to get out. If you're in a data science project, you're trying to figure out what the data is and what data can do, or you're trying to raise the prediction rate, you don't want to get your hands tied. That's not a good thing. So how do you get out of that? The first thing I would do is to acquire a vast amount of industry knowledge. They could say that, hey, maybe you should look at linear regression because linearity is a pattern that's embedded in the data set, in the variables among the features. Something like that, it's much more valuable than if you're just crunching your numbers and then you're trying to use something even more fancier. It's going to waste your time if you're doing that on yourself. And down the road, you realize that time is valuable and you don't want to spend all the time trying to work out all the possible experiments. So something like that is definitely worth your attention. Now, with that being said, I'm not saying that you shouldn't try things out. I think you should always try things out. When I get started in the first year of my machine learning journey, I think I just took the book Introduction to Statistical Learning, and then I worked out all the R scripts in the back of the book. I believe it's something like 30 to 50 pages, and these are a collection of data sets and a particular set of machine learning algorithm. These are experiments that people already tried and finished, and they put the machine learning algorithm that work the best with that data sets together, and there's a list. All the famous data set that you've seen come from that list. The IRIS data set, the UCI breast cancer data set, the credit card default data set. All these data sets, they have a particular set of algorithm that solve the puzzle. And something like that is interesting, right? Because a data set carries its own secret. And that secret comes from the background knowledge of the data, of the industry, of the particular pattern embedded in the data sets. Now, of course, it's also possible that the pattern learned from breast cancer data set, you will also see that in a credit card default data set. That's certainly a possibility. It's unlikely that's a possibility everywhere, but it's a possibility. And from that, we're getting into a deeper dive of truly the essence of doing research. And I think that's going to be much more interesting and at a rather higher level of machine learning journey. If you can figure out some sort of pattern in the data that's on a theoretical level and that happen more than often than people expected, then that's a good research topic, right? For example, in the field of research that I'm in, I work on dimension reduction. And I look at the data that have too much information and sometimes too much noisy information, but not enough sample size. And something like that is going to be problematic because think about it. It's like you're taking an exam. In the beginning of the semester, everything is easy. You're doing small quizzes, and the quiz only tests you like half a chapter. And half a chapter only have 3 to 5 theorems that you need to memorize. And then the teacher gives you 10, 20 problems to work on. And these number of practice problems are at a rather bigger number comparing to the number of theorems that you have to remember to solve the case, to solve the problems. Conversely speaking, in the end of the exam, things are much more difficult. You are tested on the entire textbook, something like 15 or 20 chapters, and each chapter has maybe 10 theorems you need to memorize. And in the final exam, before the final exam, the professor probably gives you one or two practice problems, and they probably have like 10, 20 problems. And the number of that and the number of those practice problems and the number of those practice problems relative to the number of theorems you have to memorize in the entire book, it's not going to be enough. So this sample sufficiency problem in the field of big data, it's going to be an extremely important problem. And it's likely that it will happen in breast cancer data set, and it will also happen in credit card default data set. And that's a field of research. That's a particular question that gets raised, and it points a direction of what kind of research, what kind of tool sets should you try to find to solve that problem. And that's really when research comes in. In the beginning of my machine learning AI journey, unfortunately, I didn't really know that part. I thought it's really just about playing around with different data sets and then trying to see what kind of problems, what kind of solutions that you can come up with. I thought the creativity comes in when you can magically find a beautiful, elegant solution, most likely going to be a formula, and just magically solve that data sets. That's, of course, a rather shallow point of view, especially in the beginning of machine learning and AI journey. And I myself had that view for a couple of years long. So I was walking down the journey with that view in my head, and it turned out that it's actually stopping me from moving forward. And eventually, you're going to hit a bottleneck. You can't just expect to come up with a new formula for every data set, and that formula will just magically be working for all data sets. It most likely does not work like that. But one thing I gained from that is I've seen a lot of data sets, and I've seen a wide variety of style of data sets, and that gives me some good hands-on experience to work with different data structures. And something like that is extremely important. Now we're diverging into a different technical ground. So we talked about how machine learning journey gets started, and we talked about how that can be led to research, which is on a higher level of the journey. Now we're diving into a field that is very technical, and I think it's important to bring that up. In the journey of machine learning and artificial intelligence, you're working on sets of algorithms, and that's on a very high level, right? A random forest is an algorithm. A neural network is a set of algorithms. Even something like a linear regression, there's a formula, and that can be coded in the algorithm. So you're working with sets of algorithms that's either composed of for loop or while loop, or some sort of early stops of the loop, or some sort of iteration, right? And I would say that most likely machine learning algorithms are either an iterative problem, which means you're doing something and doing something many, many times, or a convergence problem, meaning that you have some sort of setup and you're doing something many times, then that whatever this thing is will converge to a static state. It doesn't matter which way you go, it involves a lot of iterations and many, many trials. And that's really when hands-on experience of working with data structures come in. If you have a good knowledge of working with different data structures, it will really accelerate your accomplishment down the road of machine learning and artificial intelligence. It will help you to move forward much faster and much more efficient. What do I mean by that? How do you measure an algorithm, right? You measure by time and space. So once you have an algorithm, you don't want to take too much time. You don't want this algorithm to take 10 days to be able to see the results. Then what are you going to do with the 10 days, right? Sure, you can work on something else, but that result is very costly. You have to be able to wait for 10 days. You have to either go find a job or survive somewhere. Or sometimes, what if the algorithm takes months? You need to have a room there. Turn on the laptop, turn on the software, and have the thing run for a month. And are you going to pay the rent for that? So time is the most important thing when it comes to measuring the efficiency of a machine learning algorithm, or just an algorithm. And another thing is space. Common laptops, desktops, we have this thing called RAM, right? And then on top of that, we have memories. And then we can talk about CPUs, GPUs, that sort of thing. You don't really want to take that much space either. What if you're running a big data set with hundreds of thousands of samples, with hundreds of thousands of observations, and it's a recurrent neural network, which means you need to look at the timestamp in the features of your data sets, and you want to go back as old as you can. And that requires a lot of memory. And if there's a way to somehow shorten that amount of memory consumption, that's going to raise your speed. Same thing with pictures. But nowadays, the cameras can capture very high quality pictures. We're talking about 2000 by 3000 pixels. And that's a lot of pixels. And that's only one picture. What if you have thousands of pictures that have pixel size 2000 by 3000? Then that's going to be a lot of information that you're feeding into the machine all at once. And imagine you're doing nothing fancy, just a matrix multiplication on that. And what if you want to work on the convolution, right? Convolution is a particular technique that detects local information on the picture, which means the local is a relative term, right? It doesn't mean, we're not saying that a fourth of a picture is local or a third of a picture is local. It's local because it's smaller, right? How small? That's a tuning parameter. So you circle a window, and then this window will move from row 1, column 1 of that picture, that's size 2000 by 3000, and then go to row 1, column 2, and then row 1, column 3. And then once you finish the first row, it will come back to the second row, column 1, second row, column 2, and then all the way to the end. And with the pixel size, and with the size of the picture that is 2000 pixels over 3000 pixels, you can imagine the kind of for loop that we're talking about to just generate the local features using convolution techniques. And that's very costly. It's costly by time, it's also costly by space. And those are the roadblocks that you want to figure out a way to either solve or get around with down the journey in machine learning and artificial intelligence. Now, before we wrap this up, I also want to mention a little bit about the hierarchy of machine learning, and perhaps that could give you guys a little bit high-level summary of different kinds of field that can be used as R&D for yourself, or can raise some of your interest to encourage you guys to walk down a certain direction that you guys like. End of the day, it's the passion that guides us. And I think it's very costly nowadays to be able to just even to try some things out. And I don't think that's fair. So let me give you guys a small summary of the hierarchy of machine learning right here. Machine learning comes down to two branches. There's supervised machine learning and there's unsupervised machine learning. And of course, there's something else fall outside of these two branches. There's also reinforcement learning and some other more advanced learning problems that do not fall in supervised or unsupervised. But let's start with something simple. Let's say a machine learning problem, it's either supervised or unsupervised. What's the difference in that? Supervised machine learning means you have a particular target. I want to predict tomorrow's stock price. That the tomorrow's stock price is my target. If you're going to build a model, that's your Y. And then you look at the other information in your data sets, that's your X. And if you have a clear understanding of what's your X and what's your Y, that's a supervised machine learning problem. Now, conversely speaking, there's also unsupervised. The unsupervised ML problem is referring to the type of problem that you don't really have a clear goal. You don't know what's the Y target in your model. And you're really just using some sort of a non-parametric methodology to work out some of the patterns in your data sets. K-means can be non-parametric. A principal component can be non-parametric. These tools allow us to be able to see what are the patterns in your data without a particular target. Now there's a field research that's specifically dedicated to a technique called variational autoencoder, VAE. That's technically speaking also unsupervised because we're not really looking at labels in VAE. So now we have a first level, supervised or unsupervised. Let's talk about supervised. Down to the next level of hierarchy, you can separate the supervised machine learning problem into continuous and discrete. What do I mean by that? If your target Y is continuous, temperature, stock price, stock returns. From a mathematical standpoint, a stock return can be 2%, can be 2.1%, can be 2.11%. So now you get the idea. If you can infinitely go down further, then it's really considered continuous because it's a numeric number. Now, converse to that, there's also a discrete variable. If your target is discrete variable, you're in the field that is essentially a classification problem. Now, what do I mean by that? If we have a bunch of pictures and the labels are cats and dogs, then the label is just going to be cats or dogs. Right? It's 1 that is cat, with 0 that is not cat. which means dogs, because there are only two possibilities. So in that sense, there isn't really 1.2 or 1.22, something like that. It's just 1 or 2. That's a classification problem. And in particular, it's a two-class classification problem. And from there, we can talk about overfitting, underfitting. We can talk about if there's any regularization term that we can use, if there's a dimension reduction that we can use, if there is any feature engineering tools we can use. And that's when everything comes together to help you solve a particular problem. The reason that people separates the supervised machine learning algorithm into two branches, the continuous version, which is called regression problem, or discrete version, which is called classification problem, is because the loss function are different. The loss function is essentially a formula that compares your educated guess on that target and the actual real value provided by the data of that target. And the classification problem has their own error function, and so is the regression problem. In machine learning, the loss function is everything. It tells us where your mistake is in your educated guesses of your machine, and it tells you where you can go from there by taking the gradients. Now, with that being said, that wraps up the hierarchy of machine learning problems. So now we're at the end of this presentation. Now, the biggest takeaway I want you guys to have is this water principle that I've adopted down the journey of machine learning. What do I mean by that? If you put water into a cup, it becomes a cup. If you put water into a teapot, it becomes a teapot. Now, water can flow or drift or crash. So you want to be water, and you want to do your best to be water. And it goes exactly the same in machine learning and also in your life. It's really about putting all different sources together to form something organic, to form something that's applicable to yourself. And that's really when the essence of water principle comes in, down the journey of machine learning and artificial intelligence. Thank you very much. If you like this speech, please feel free to go on LinkedIn to add me as a connection. I would love to talk to you guys more. If you guys have questions, I'm happy to answer that. You can also go to my website, and I had a lot of fun being here to share with you guys some of the roadblocks I've seen in the past. I believe it's important to share my mistakes so that you guys don't necessarily have to make them again. So I hope you liked today's speech. Thank you very much.